Hello everyone, this is lecture 3.2. So lecture 3.2 continues with the linear algebraic equations, and what we're going to be looking at mainly is LU decomposition after we have completed Gauss elimination and Cramer's rule. In lecture 3.3 we'll focus on matrix inversion, and then 3.4 we'll do Gauss-Seidel and Gauss-Seidel relaxation. The reason why I have these both in the same color is because they're kind of, directly related to each other. Once you know LU decomposition, then we can move on to matrix inversion using the LU matrices. All right, so we're going to do some solving for basically a system of linear equations in a way where we decompose the coefficient matrix A into a lower triangular matrix and an upper triangular matrix. So what is a lower triangular matrix? Basically, this is what it is. You have the identity matrix, so one's all the way across. You have zeros on top, and then you have three components here, which basically you have to figure out what they are. And then the upper triangular matrix, we kind of saw how to get this using Gauss elimination. And for our 3x3, we used the three-step method as we saw in the previous lecture. So now we're going to do some work on Blackboard or Drawboard, and we'll start off with LU decomposition, and then for lecture 3.3, we'll look at matrix inversion. All right, so this is the board work for lecture 3.2, which is focused on LU decomposition. As we mentioned before, we can break down a system of linear equations into the form of AX equals B, where A is the basically coefficient matrix, X is a vector of the unknown variable, and then B is a vector of some constants. All right, so now we're going to decompose this matrix A, which is the coefficient matrix, into a lower triangular matrix and an upper triangular matrix. So the upper triangular, as I mentioned before, is solved using Gauss elimination. And then the lower triangular is solved using the steps we took to get the actual upper triangular matrix, and you'll see how we do that in a second. Once we have L and U, right, then we can basically write this format of AX equals B in a new form, which is LU X equals B. And the point here, we're going to solve for a variable called D first. So we're going to call UX as D, and then this basically causes this expression to be LD equals B. Then we solve for D. Once we know D, then what we do is go back and solve for X in the expression, which is D equals UX. So again, just to repeat, what we're doing here is we're going to let D equals UX. Then we're going to solve for D using forward substitution. And then using UX equals D, we're going to solve for X using backward substitution. So you could probably see this best when we do an example, but essentially, when we let D equals X, we're going to use this expression to solve for D. And then afterwards, once D is known, then we plug it into this equation here, and we solve for X, because the upper triangular would be known, D would be known, and the only unknown would be the X using backward substitution. All right, so let's do an example. So let's say we have a set of three algebraic linear equations, x1 equal minus x2 plus x3 equals 1. Then we have negative x1 plus 3x2 minus 2x3 equals 1. And the third one, x1 minus 3x2 plus 4x3 equals 2. So these are basically the three equations with the three unknowns. And from here, we're going to basically extract the coefficient matrix so that we can learn how to do LU decomposition from this example. So the coefficients are, as we can see here, as a 1, -1, and 1. So we're going to write these here, 1, -1, and 1. And following the second equation, -1, 3, and -2. And then the third equation, 1, -3, and 4. So this is our coefficient matrix. And our initial goal here is to find what is the upper triangular matrix using Gauss elimination. So initial goal, find upper triangular, which is represented with capital U. So how do we do this? Again, Gauss elimination follows basically row operations. So we're going to have to do some row operations on this matrix. So we can write here our row operations, and we're going to do the steps here on the left side, and we'll kind of show the matrix as it changes as we do those row operations. So as you recall, the first row is typically unchanged. Then we have the second row is going to be modified using the first row. Also, the third row is going to be modified using the first row. Always in the first two steps. We use the first row to modify the other rows. So row 2 is going to equal some multiple of row 1 plus row 2. Again, row 3 is going to be equal to some multiple of row 1 plus row 3 to achieve zeros, right, in this position and in this position. So what factors would we use in this case? Just adding row 1 to row 2 will end up with a 0 here because the second row is already a -1 and the first row. So all we need here is basically a 1. And then for the third row, we need just a -1 to cause row 1 to eliminate basically the 1 in the third row on the bottom left. So this would result in a matrix that looks like this. So we're going to have the first row unchanged. Second row, we're going to have a 0 here. We're going to have a 2 here, and then a -1 here. And then the third row, we have a 0, -2, and 3. So now we do the final row operation, which will basically cause this point here to become a 0 using the second row. And in this case, we're modifying row 3, and we're going to use some multiple of the second row added to row 3 to do this modification. In this case, we have a 2 here and a -2 here, so all we need to do is multiply by 1. And this will result in a matrix that looks like this. So we're going to have 1, -1, and 1, 0, 2, and -1. So the first two rows are unchanged. And the last row, we just did this row operation to have two zeros in here with a 2 as the final variable or value. So this is the upper triangular matrix. This right here. This is the U matrix. In terms of the steps, we can write them in terms of an elementary matrix. So we have 3 row operations. Each one of these steps can be represented by a basically elementary matrix. So, and if we represent these with elementary matrices, basically what we're saying is if we have M1 multiplied by M2, so this would be the first row operation, this would be the second row operation, and then M3 multiplied by the coefficient matrix A, we get the upper triangular matrix. So again, let me write this in terms of words. So in terms of the steps, we can write them in terms of an elementary matrix. So in this example, we had 3 row operations, and as I mentioned, This would be one elementary matrix, it would be a second, and this would be a third. And each one of these represents a row operation, all right? So, and what is an elementary matrix? Essentially, an elementary matrix is an identity matrix with one single elementary row operation. So in this case, the inverse of the elementary matrices will give us the lower triangular matrix. All right? So the key thing here is the inverse of the elementary matrix, all of them combined, will give us L, which is the lower triangular matrix. So how does that look like in terms of an equation? So basically, like I said before, if I have one row operation or one elementary matrix, a second one, and then a third one, because in this case we have 3 row operations multiplied by the coefficient matrix, this gives us the upper triangular. And then if I take the inverse of all of these, so I'm going to say A is going to be equal M1 inverse, M2 inverse, M3 inverse, multiplied by the upper triangular. This here, right, would be my lower triangular matrix. So then what we end up with is basically A is equal to LU, and this is basically the decomposition of A into L and U. So let's find L, given that we've done all these row operations here to get the upper triangular. And like we mentioned before, every one of these steps is what we're going to use to find that lower triangular matrix by developing these elementary matrices for each row operation to give us the lower triangular matrix by taking the inverse of each one of these elementary matrices. So just as a side note, I want to mention, again, if we had the identity matrix, so the identity matrix, again, is just a ones across the diagonal and then zeros everywhere. And I multiply this with my, coefficient matrix, which is 1, -1, 1, -1, 3, and -2, and so on. What we get in this row operation here, or this matrix operation, when we're multiplying these two, what we're doing is we're doing this row multiplied by this column to give us essentially the element in this first box. All right? So 1 times 1 plus 0 times 1 plus 0 times 1 will give us essentially just a 1 here. You do the same thing for every, right, row here. So if I want to do this row also with this column, what we're going to get is the value here. So we're going to get 0 times 1, 1 times -1, and 0 times 1, which gives us -1. Essentially what's happening here is we are just going to get the same exact matrix if we multiply the identity matrix, right, with this coefficient matrix A, we will still end up with basically A. So in the elementary matrix, what we're doing is we have an identity matrix and we modify one of those elements in there to do the row operation that we want, which combines, say, row 1 with row 2, or row 2 with row 3, and so on. All right, so let's find L in this case. So let's just do a line here and then focus on finding L, which is the lower triangular matrix. So step 1, right, if you recall, was basically row 2 is equal to, let's put an equal sign here, row 1 plus row 2. So M1 in this case, which is the elementary matrix for the first row operation, is going to be the identity matrix. So we have the identity matrix with the zeros here. And the only thing we're going to modify in here is the element that we see right here in this box, right? Because this is basically doing a row operation where if I take, a value here, so in this case, we're doing row 1 plus row 2 to modify row 2. What we're doing is we're going to put here essentially a 1 and then zeros everywhere else. And what this is doing is exactly what this row operation does, but in matrix form. So if I look at, the matrix A, for example, let's take this as an example here. So if I do M1 multiplied by A, right, what we're doing here is the following. So 1, 0, 0, 1, 1, 0, 0, 0, 1. And then let's put the matrix A here. We have 1, negative 1, 1, negative 1, 3, negative 2, 1, negative 3, and 4. So what we're doing, right, in the first column here, or first row, when I multiply by this, nothing changes. When I multiply by this, nothing changes. When I multiply by this, nothing changes. So the first row will be basically unchanged. So we're going to get 1, negative 1, and 1. Then we go to the second row. So the second row, we're going to be doing this operation here. And what we're getting is that I'm multiplying this 1 by the first row plus second row multiplied by 1, which is doing row 1 plus row 2. So when we do that, we basically are going to get, right, what we got before, which is a 0 here, and then we had a 2 here, and then we had a negative 1 here. And then for the last row, in this case, we're doing 0, 0, 1 multiplied again by this column here, and we're just going to get a 1, a negative 3, and a 4, meaning that we haven't changed the last row, because this elementary matrix is only focused on one row operation, which is R2 equals R1 plus R2. So then we would get 1, negative 3, and 4. So that's unchanged. So here, basically, I'm just showing you how this elementary matrix is doing the row operation that we see up here. So now we understand that. So let's move on and into step 2. All right, so again, this would be considered here as another kind of side note. All right, so let's do step 2 now, which was row 3 equals to negative row 1 plus row 3. So that's what we did. If we recall, let's go back. We can see this up here. So we did row 3, right, equals negative 1 R1 plus R3. All right, so in terms of an elementary matrix, this is going to look like, again, we draw the identity matrix with the upper part all being zeros. And what we're doing is we're changing row 3. So row 2 here, the 0 will be the same. And what we're doing is we're using row 1. So then we would use the first column, right? If we were using row 2, then we would use the second column. But in this case, we're using row 1 to change row 3. So then this would be a 0. And then whatever coefficient we have here, in this case, it's a negative 1, we would write here. And this would be our second elementary matrix. And then step 3, we're going to have row 3 equals row 2 plus row 3. And then in terms of an elementary matrix, this is going to be M3 because this is our third step. And in terms of what we're going to start with is the identity matrix with zeros here. And in this case, we're modifying row 3. So then the first 2 rows are still the same as the identity matrix. we're using, in this case, the second row. So that means the first column is going to be a 0. And what we're doing is second plus 3, so we're modifying this part here. And in this case, the coefficient is just 1. So then we put a 1 here, and this would be the third elementary matrix. So now the goal is to find the L, right, lower triangular matrix. And what we need is to find the inverse of each one of these elementary matrices. So now we have M1, M2, and M3. For L, what we need is basically the inverse of each one of those. So M2, M1 inverse, M2 inverse, and M3 inverse. And basically for an elementary matrix, the inverse is the identity matrix with the sign of the single row operation switched. All right, so let's write that in words. So the inverse of an elementary matrix is the identity matrix with the sign of the single row operation switched. So as an example, right, if it was 1, then you make it a -1, right? So that's basically what we're saying when we're saying to switch, right, the sign of the single row operation. So for M1, in this case, so M1, if you recall, was just 1, 1, 1, 0, 0, 0, and then we had a 1 here, and then we had zeros everywhere else. So the inverse in this case, right, so M1 inverse is going to equal 1, 1, 1, 0, 0, 0, 0, 0, and the only thing we're going to be changing is the sign, so we're going to have a -1 here instead, and this is the inverse. Similarly, right, M2 is equal to 1, 1, 1, 0, 0, 0, and then a 0 here and a 0 here, and this was a -1 here. So then M2 inverse is going to be, again, the same matrix, but the sign of the single row operation switched. So we're going to have a 1 here instead of a -1. All right, so then M3, in the same fashion, M3 inverse is equal to 1, 1, 1, 0, 0, 0, 0, 0, and then the single row operation was a 1, so then we're going to make it a -1, and that would be the third, basically, elementary matrix inverse. So now L is going to be multiplying all of these together, right? So L is equal to M1 inverse times M2 inverse times M3 inverse, which is essentially the identity matrix. So 1, 1, 1, 0, 0, 0, right? With whatever values we have in here in these inverses plugged in directly into here. So this position has a -1, we're going to put a -1 here. This position has a 1, we're going to put a 1 here. This one is a -1, we're going to put a -1 here. And this would be basically the lower triangular matrix. So now what we're going to do is work towards, using these decomposed coefficient matrix A, LU, to solve for the unknown variables x1, x2, and x3. All right, so let's do that now, where we're going to be doing basically backward substitution and forward substitution. All right, so we have ax equals b, and now we decompose it into LU, x equals b. And if you recall, we're going to let ux equal d, And this will give us, in this case, this part here will give us LD equals B. And then we're going to solve for D first, and then solve for X afterwards. So from here, we're going to start off with LD equals B. All right, and then we're going to plug in our lower triangular matrix. So in this case, our lower triangular is 1, -1, and 1, 0, 1, -1, and then 0, 0, 1. And then the D matrix is just going to be something that's unknown, so we can write D11, D21, and D31. And then the B matrix is what this is equal to, which is 1, 1, and 2 in this given problem. So this would be going back all the way to the beginning to this, where we have the 1, 1, and 2, and that's where the D matrix, or sorry, the B matrix comes from. So this is, basically the B, this is the D, and this is our lower triangular matrix. So just like we did before, in this case, we're going to be looking at the first row first, because that's where most of the zeros are. So looking at this first row here, what we have is D11 plus 0 times D21, which is 0, plus 0 times D31, which is also 0. And this will give us the value 1, as we see here. So then D11 is equal to 1. Similarly, we look at D21 in the bottom. So now we're going to look at this second row here. Let's use another color. Let's just look at this second row. We're going to have negative 1 times D11. So this is negative D11. Plus 1 times D21. So this is D21. Plus 0 times D31, which is 0. And this will give us 1. So now what we do is we plug in 1 for D11, and we solve for D21. In this case, we get the value of 2. Then for the last row, right here, we have basically D11 minus D21 plus D31 equals 2. And then in here, we're going to plug in 1 for D11 and 2 for D21, and then solve for D31, which in this case is going to be just equal to 3. So now we have solved for this vector D, which we're going to use to solve for the unknown variables x1, x2, and x3. So in this case, right, we have this matrix or this vector D11, D21, D31, and this is equal to 1, 2, 3. All right, so now we're going to look at the second part of solving for the x, where we have ux equals d, right? If you remember from before, we have ux right here equals d. So we have our upper triangular matrix, which we solved for before. So we have 1, -1, and 1, 0, 2, and -1, and then 0, 0, 2. Multiplied by the unknowns x11, x21, and x31. And this is equal to our matrix or vector D, which is 1, 2, 3. So now we're going to apply, right, backward substitution to solve for the unknown values. So just like we did before, if you recall from the previous lecture, right, x31 is going to equal to 1 over the coefficient, so this is a half, multiplied by 3. This will give us 3 over 2. And then looking at x21, we're going to do 1 over the coefficient. In this case, it's also a 2, multiplied by the 2 we see on the far end here, minus, right, the -1, multiplied by x31, which we solved for in the previous step. So then we plug in 3 over 2 here, and then we do the math, and what we get is half is going to equal to essentially 4 over 2 plus 3 over 2, which gives us 7 over 4. And then x11 is going to be 1 over 1, which is the coefficient there. Then we have a 1 here, minus -1 times x21, minus 1 times x31, and this would give us the result. So this here is 7 over 4, and then this here is 3 over 2. Then you do the math in here, so you're going to have essentially, 4 over 4 plus 7 over 4 minus 6 over 4 by doing this common denominator, and then we get that the value of x11 is 5 over 4. So now we've solved for the unknown x values using LU decomposition for this given problem. So the advantage of having, LU decomposition is that if I have this coefficient matrix A, which is unchanging, where I only change basically the B vector. So if we go look back, if we have a set of problems where this coefficient matrix is always the same, but I have a different set of B values right here, then I can simply perform the same operations that we just did, right, on all the problems with the different values in this B vector. So that is one of the advantages of using LU decomposition. All right, so let's write that in words. So down here, we're going to say, the fact we have ln u, we can solve any system with the same coefficient matrix A with different sets of B values. And this will help us in basically solving for the inverse, as we're going to see in the next lecture, which is lecture 3.3. Before we get there, I have a small problem for you guys to try to solve and just to practice what we did. So basically, practice problem. So for the system, or for the same given system, solve for x given the following. All right. So you should do this, using LU decomposition, and the result, or the answer in this case, would be x11, x21, x31 is going to equal 5, 7, and 6. All right. So try this out, and we'll see you in the next lecture on solving for the inverse using LU decomposition.